All right, hello. This is our first video lecture. The overall topic is predicting physical properties, and this will be lecture number 1, which is basically on polarity and this concept of polarity. What you should do is copy down everything on the board. I'll get out of the way and you can pause it, and we'll go through these. So, as it says, physical properties of compounds. So, molecules, it's basically their bulk properties. So, not a single molecule, but many molecules of the same exact compound will have these properties in bulk. But they can be predicted by their structure, which is important for this class. Examples of physical properties are melting point, so that's the temperature at which a substance will melt. Boiling point, so that's again the temperature at which a substance will go from the liquid phase to the gas phase. For melting, we're talking about going from a solid to a liquid. Another example of a physical property is solubility. Solubility is how something dissolves, how much of something dissolves. So for example, salt dissolves easily in water, and so does sugar. And these are really completely different molecules. And you may notice that salt dissolves a lot faster than sugar does in water. But water's not the only thing that things can be soluble in. There's a wide variety of different solvents. Many of them are organic molecules that are liquids that can dissolve different things with different properties. Another common property is odor, or the smell of something. That's a physical property. And we'll address this when we talk about different functional groups. So certain functional groups have really characteristic odors, especially amines or anything containing sulfur, like a thiol or a thioether. And then even color, and we'll discuss color later on in the course. The most important concept in predicting physical properties is polarity. And basically here we're going to talk about individual bonds and whether or not they're polar. A bond is considered polar if the two atoms that are connected have basically a large difference in electronegativity. And so we've discussed electronegativity a little bit. Normally you would calculate the difference, but rather than working with numbers, essentially I'll give you some guidelines as to what makes a large difference in electronegativity, or what bonds have a large difference in electronegativity between the two atoms bonded together. And so if we think about this, in the periodic table, we know in one corner we have fluorine, and that's the most electronegative atom. The two elements next to fluorine in the periodic table, besides the noble gases, are oxygen to the left and chlorine below. And these would be essentially the second most electronegative elements. And so as we get further away from fluorine, we get less and less electronegative. And that's something we've already learned. And so basically as you move away from fluorine, you're getting less electronegative. And I'll draw hydrogen in here without drawing in the rest of the periodic table. Hydrogen, although it's represented quite far away from fluorine, actually has a decent electronegativity, and it's kind of a special element. But we'll address that. what you'll need to know are some common polar bonds, and these are going to show up all over the place in organic molecules. For example, well, one that doesn't show up all over the place but involves fluorine, which is kind of rare, would be a carbon-fluorine bond. So this is a very polar bond. Fluorine is the most electronegative element, and carbon is relatively far away, several atoms away from fluorine. And so this large electronegativity difference means fluorine is better at attracting electrons to it than carbon. And so that means the electrons, which we know are negatively charged particles, will be more around fluorine and less around carbon. And this makes that bond polar, just like a magnet. And we'll get to assigning plus and minus charges soon enough. Another example of a polar bond is a carbon-oxygen bond. And it's not as polar, but it's still a polar bond because oxygen is really pretty electronegative. Also in this category, even though they're right next to each other in the periodic table, a carbon-nitrogen bond is barely polar enough to be considered a polar bond. Also, hydrogen-oxygen bonds and hydrogen-nitrogen bonds are polar bonds. A hydrogen-fluorine bond is also very, very polar. However, a hydrogen-fluorine bond will not be observed in an organic molecule, so I won't put it up there. But these are all ones you should know as polar bonds. Incidentally, they don't have to be single bonds. So for example, a carbon-oxygen double bond, which we know is a carbonyl, is also a very polar bond, just like a carbon-oxygen single bond. Likewise for nitrogen, you can have carbon-nitrogen double bonds or carbon-nitrogen triple bonds, and these are both polar bonds. Now, you can't have a double bond to hydrogen because hydrogen can only have one bond. And so those cases are a bit simpler. This statement is really important. Make sure you copy it down. This gets at the term polarity or polar, which means it's going to involve knowledge of some positive and negative charges. What would we think about possibly, based on some of these examples, do you think that HCl would be a polar bond? What about a carbon-chlorine bond? Would that be a polar bond? Well, we can look at our excerpt from the periodic table. Well, chlorine is very close to fluorine, very similar in electronegativity to oxygen. And so, yes, These are both also polar bonds, and I didn't include them in this list. They're not as commonly observed, but those would be polar bonds too. Well, this begs the question, if it's not a polar bond, then what is it? If a bond is not termed or defined as a polar bond, then it's a nonpolar bond. And these are really the only two classes. Certainly some polar bonds are more polar than others. But nonpolar bonds in general are all less polar than any polar bond. Typical nonpolar bonds are carbon-carbon bonds or carbon-hydrogen bonds, which we'll see a lot of in organic molecules. And so a carbon-carbon single bond also means a carbon-carbon double bond or a carbon-carbon triple bond can be nonpolar. So these are our nonpolar bonds. And in fact, any atom that's bonded to itself will be a nonpolar bond. For example, in the air we breathe, the molecule oxygen is nonpolar. And so is the molecule nitrogen, because the same element's bonded to itself, so there's no difference in electronegativity. So these are both nonpolar molecules because of that nonpolar bond. So we'll look at some examples. And the first one we can look at is a vital molecule. And that's water. And so water is composed of only hydrogen-oxygen bonds. These have been defined for us as polar bonds because oxygen is much more electronegative than hydrogen. It's much better at attracting electrons to itself. And so since the bond is composed of electrons, it means oxygen will attract those electrons to itself more so than hydrogen will. And so what that results in these polar bonds is a buildup of electron density, which means the electrons are closer to oxygen in those bonds than they are to hydrogen. Even though the two molecules are sharing those electrons, they're closer to oxygen. And because they're closer to oxygen and electrons are negative, then that means that oxygen itself will actually have a partial negative charge. The way we represent this as chemists is we draw a lowercase delta, the Greek letter, and then the negative sign, or a minus sign. Nitrogen, since the electrons in the bond are closer to oxygen, then that means that they're not as close to hydrogen, and so hydrogen, since the negatively charged particles are further away, hydrogen will be positive. And so we represent this, again, with a lowercase delta, but a plus sign. And so the hydrogens are both a little bit positive, and the oxygen is a little bit negative. And so this is what we mean by polarity. There's a difference in the electron distribution which makes positive and negative charges. And so just like a magnet works, and you can feel in a macroscopic world the force of those charges, the same is true in a molecule. And so this difference in charges allows these things to have strong interactions with other molecules, and we'll get to that. This symbol, a lowercase delta, in chemistry will always refer to a partial something. Essentially, for us, it will always be a partial charge. And so it means it's not a full charge, like we've been exposed to iron 2 plus or iron 3 plus or Cl minus. And these can form ionic compounds. But for example, Cl minus, the ion, which looks like this, that negative charge is a full -1 charge. And so that's a significant negative charge. When we talk about partial charges, we're talking about between a neutral atom and a negative charge of 1. So somewhere in between a full positive or negative charge. So we can look at some other molecules. Here's an example. What you want to do is label the polar bonds and then try and label where there's going to be a partial positive or a partial negative charge. And they won't necessarily be everywhere, only on atoms involved in polar bonds. Here's another example. So go ahead and try and label those. You can pause the video. In this example here, we've got nitrogen, which we should recognize as one of our electronegative elements. So from our short list, we know carbon-nitrogen bonds and nitrogen-hydrogen bonds are polar bonds. And so we have a polar bond here, we have a polar bond here, we have a polar bond here. Bonds that are not recognized as polar, hydrogen-carbon bonds, or carbon-hydrogen bonds, would be nonpolar bonds. And so I'm going to color in the polar bonds in red to indicate them as polar bonds. Now, if we want, whenever we have polar bonds, we should think about partial charges. It's the more electronegative element that'll have the negative charge, and the less electronegative elements will have a positive charge. Since nitrogen is the closest one on the periodic table to fluorine, it's easy to tell. So nitrogen will have the partial negative charge, then all of these other elements bonded to it that are less electronegative will have a partial positive charge. And what that means, again, is that the electrons in this bond, since those are negatively charged, are going to be closer to the more electronegative element, and that's a buildup of electron density, which causes it to be partially negative. The other atoms then are partially positive. And the molecule is overall neutral, but it has areas in it that are more positive or more negative. If we look at this molecule here, which is methane, well, it's composed completely of nonpolar bonds. So there are no partial charges to label, so it's done. The last thing that I would like you to do is try 3 more examples, and then I can go through them. But definitely give it an attempt. Don't just wait for the solution. Pause the video, try and label them and understand, and then I'll go through it and explain. So here's our 3 molecules. This first one is acetone. You don't need to know that, but this is the molecule, again, that's in nail polish remover. So think about nail polish remover, and we'll get into these properties, but that's a solvent. So it's a solvent specifically for nail polish, to dissolve the nail polish and give you the opportunity to put a different color on there. The properties of acetone as a solvent come from the nature of its bonds that make it up. And so as we see here, acetone has a very polar carbon-oxygen, in this case double bond. So I'll put that in red. So this is our polar bond. And then the other bonds are carbon-carbon or carbon-hydrogen bonds, so those are non-polar in nature. And so acetone really only has one polar bond. Now it's a pretty significant polar bond, and if we label charges, we know that oxygen is more electronegative, so it's a partial minus charge, and carbon then is a partial positive charge. And that's it for this structure. But acetone is a good solvent because it has a polar bond, which makes that whole region of the molecule polar, and then it has a non-polar region. And we'll get to why that affects solubility in the next lecture. This molecule, and first of all, we should name the functional groups too. If you didn't identify the functional groups in these molecules, you should go ahead and do that now. Acetone is a ketone. This molecule here is an ether because it's an oxygen sandwiched between 2 carbon groups, and it's just single bonds. Well, again, it's another compound with oxygen, and so these would be our polar bonds. And the rest of the bonds here would be nonpolar. And so we could expect, again, partially negative charge on oxygen and partially positive charges on these two carbons. And so the hydrogens in the structure all are essentially neutral, and this carbon over here, because they just have nonpolar bonds. Over here, the functional group would be an amide. And specifically, since the nitrogen's bonded to two carbons, that would be a secondary amide. Now, we've got two different electronegative atoms in the structure. And so if we want to identify polar bonds, here we have an oxygen, so certainly this will be a polar bond because oxygen is bonded to carbon, which is much less electronegative. And the carbon-nitrogen bond here will also be a polar bond. The nitrogen-carbon bond here will also be a polar bond. And then the nitrogen-hydrogen bond is also a polar bond. Now what we would expect when labeling this structure is that we would have a partially negative charge on oxygen and a partially positive charge on this carbon. Based on this analysis, we would expect a partially negative charge on this nitrogen and a partially positive charge on hydrogen and a partially positive charge over here. So the partial negatives are on the electronegative elements, the partial positives are on the elements or atoms bonded to those electronegative ones. So this is good practice.